So this presentation is based on two papers. One is, both are related to the symmetry defense against adversarial perturbation attacks. One of the papers is based on CNNs, and the other one is based on XGBoost. For those who are unfamiliar with the domain of adversarial perturbation attacks, and specifically on CNNs, there's this famous image where you see that you start from an original image, and then you add some little perturbation, which is basically imperceptible to the human eye, and yet it can cause misclassification to classifiers. And the basic blueprint for how such attacks are constructed, how these adversarial samples are constructed, is exactly this. So you start from an original sample, and then you try to go towards the classifier boundary so as to cross it just a little bit so as to cause misclassification. Now, this may seem like, innocent enough. We have a panda that doesn't look anymore as a panda, so what is the big deal? The big deal is that such classifiers and AI systems, which are based on classification, are being increasingly deployed in real-world scenarios where it matters what the output is. For example, we can have an autonomous driving vehicle which relies on a classifier in order to distinguish between traffic signs. And so, of course, we do not want to have a stop sign being classified as 80 miles per hour sign or vice versa. Another setting is we have malware, and malware we have classifiers that classify malware, and of course we want to be able to tell virus files from non-virus files. And a recent development related to this is also large language models, because they can be used to basically go from adversarial features to actual files. And this has been, so far, before LLMs, this was kind of a stumbling block in the way of automating the creation of malware. But the introduction of LLMs now, or the recent success of LLMs, has made this actually a concern. And so another domain where this could be an issue is, for example, we have all these generative AI solutions that are coming up, but they do rely on images that they get from the internet. And we can imagine that we can have their unreliable images, adversarial images, and it would be good for generative AI to function well, to be able to tell whether an image is a panda, or is it a gibbon, or is it a stop sign, or something else, and so on. The thing is that the reason this is a problem is also because there is no good solution so far. So the best current solution is adversarial training, which was mentioned in a previous I think in the previous presentation. So basically what it does is it trains with adversarial samples that are classified correctly. And the main reason why this doesn't work is because it requires that you know in advance the attack, which in real world scenarios, it's simply not possible. And so, but even if you could get around that you could train with using another attack, still you need to know the ballpark of the perturbation values, and that's again not available. And even if you know the exact attack and also the perturbation values, the accuracy can go down close to zero. So basically this means that we do not have a solution, and this is a problem. Those who study computer vision are generally come out of it basically learning that CNNs handle symmetry well. So CNNs use convolutional layers, which are basically designed to handle translations or shifts, which means that if you have a teapot, for example, in one corner of the image and you move it to the other corner, CNNs should be able to handle it. And in general, the blueprint for the construction of CNNs is that it's this layer of equivariant layers. And what does equivariant layer mean? In general, a function, and we can think of the layers of the convolutional layers, or in general, a function is equivariant with respect to a symmetric transformation if we can apply either the function or the symmetry, if we can interchange their places. So it doesn't matter whether the symmetry is applied first or the function. And so yeah, the design is so that CNN handles the translation symmetry, and in addition we have the usage of data augmentation, which uses, for example, a horizontal shift of images so that the teapot in this case can be classified correctly, whether it's one way or the other. Or the same can be done for small rotations, where if the teapot is slightly tilted, we'd be able to handle it. So the CNN would classify it correctly. But of course, there's always, however, in reality, CNNs cannot handle symmetry well. And this is quite unfortunate, since in nature, symmetry is pervasive. So this is a quite fundamental thing not to be able to handle well. And how do we know? Well, occasionally for original images, what we get is that symmetric images can classify the same. And one simple way to see this is if you are testing a model, and if you, let's say, in the case of images, you simply flip all the images, you can see that the accuracy is going to be different for the whether you're testing the original images or the symmetric images. Now, in terms of adversarial samples, what this means is that, or what this might mean is that if we apply symmetry to adversarial samples, which to begin with classify incorrectly, it means that we have a chance here that maybe the classification of symmetric adversarial samples can revert to the correct classification. And so let's see whether this holds. This may seem a bit complicated as a slide, but I will walk you through it. So just a reminder of what equivariance means, that you can apply either the function or the transformation first. Now here we change the problem a bit, that we do not look at the output, the classification of the output for CNN, but here we look at the output as what the classifier boundary is that a CNN produces. And so the fact that the classification of samples in CNNs for symmetric samples is different basically means that in symmetric settings, the classifier boundary will be different. Because if the classifier boundary was the same in symmetric settings, or more formally, in equivariant settings, then the classification of samples would not be different. So we would get the same output. So here, if we start from in the figure, from the left lower corner, we have our data set shown by just one sample for each class. And if we go first applying the function along the bottom to the right, we apply the function and we get a classifier boundary. And then going upwards, we then apply the symmetry. And in this case, the symmetry is inversion, where each feature value is substituted with 1 minus the feature value. And so if we go bottom and top, then we will get a different output from what we would get if we apply the symmetry first, going first up, and then applying the classification in order to find the classifying boundary. So yes, we conclude that we find different boundaries in equivariant settings. But now, what does this mean and why is this important? This is important because, as I explained in the second slide, adversarial attacks basically use the classification boundary in order to construct the adversarial samples. So they start from an original sample and then they move towards this boundary in order to cross it, to go just beyond it and to cause misclassification. So if the boundary is different, the attacks are going to find different adversarial samples in equivariant settings. So then the question is that, are these adversarial samples, if we carry them from one setting to the other, are they still going to be adversarial or not? We conduct experiments, so moving on to experiments. In this case, we have adversaries that are zero knowledge, so they're not aware of the attack. And here we use, well, for all experiments, we are experimenting with ImageNet, ResNet 50 model, and we make no changes to the model or parameters. And in this case, because we're using the horizontal flipping symmetry and ResNet 50 is trained by default with data augmentation with horizontal flipping. In this case, we do not even need to do anything to the model to train with any extra samples. So simply flipping the adversarial sample makes the samples non-adversarial anymore, and we go from 0%, which is under attack, we go to close to default accuracies over 70 for many attacks. And again, what is important here is that no attack knowledge is used, and the defense counters different types of attacks. The same, we also apply the same for zero knowledge adversaries using another symmetry in order to show that this defense can work also for data sets which do not have inherent symmetries. So in this case, we use two different models. One model is the default model, and another model is the same in terms of model and parameters, but it's just trained with only inverted samples. So in this case, what happens is the zero knowledge adversary is not aware. So they generate the adversarial sample based on the model they know about, and then we get the adversarial sample, we apply the symmetry and simply classify it with the other model. And here also the accuracies go from 0 in the case of 0 for most cases, and go from 0 to close to default accuracies, near default accuracies. And again, no attack knowledge is used, and different kinds of attacks are handled. Now the question is, what do we do then if the attacker is aware of the defense? Well, we have a perfect knowledge adversary. So in this case, one symmetry would not be enough, because the adversary can simply apply the symmetry before they hand over the adversarial sample to us. And then when we apply the same symmetry again, the two transformations are going to cancel each other, and so then we would have the original adversarial sample. So in this case, we basically create a symmetry group. In this case, we use the horizontal flipping symmetry and the inversion symmetry, the same ones that I just discussed. So basically, the aim of the symmetry group, based on its what is called closure property, the aim is to confine what the adversary can do, because whatever transformations they can apply here, which are identity, basically doing nothing, flipping, inverting, or flipping and inverting, whatever they apply, you can see here that there is only these four types of images that the adversary can work with. So, and even if they apply consecutive transformations, it remains within these. So basically, it confines what the attacker can do, and also it confines the experiments that we need to do to show that actually the defense works. And here there's an outline of the attacker can do, but also showing here that at the very bottom, there's what happens if there is no attack. And from the point of view of the defense, every sample that we try to classify is handled exactly the same. So it doesn't make any difference whether the sample is adversarial or not. So here we have that we have the stage where the adversary generates the image, the adversarial image, but before that, they can do whatever transformations they want within the symmetry subgroup. And they can also do these transformations after the generation of the adversarial sample, but actually they don't need to, because in the evaluation, in the classification of the samples, the defense actually does generate all 4 symmetries of the subgroup of any image that it gets. So, and even if the attacker tries to switch to one of the other symmetry cases, it wouldn't make any difference, because the defense would get these 4 that you see on the right-hand side. The defense would get the same samples in any case. So basically, we have an adversarial sample, we generate all 4 symmetries of it, and then we classify all 4. We get 4 labels, and we decide on a final label, so to speak, based on 2 labels agreeing, based on 2 labels of these symmetric adversarial images agreeing with each other on the output label of the sample. And again, here I'm presenting the table. I omitted it for the previous cases. So you can see we have different types of attacks with different kinds of 2 types of perturbations, L2 and L infinity. And the 4 columns on the right, they are for all the 4 cases where the adversary starts either from original image, so identity symmetry, flipped image, inverted images, or flipped and inverted. And with a default accuracy of 77%, you can see that for many cases, the resulting accuracy is very close to the default accuracy. Now, there is one more thing that we need to consider when we make a defense, is that what if the attacker adapts their attack now that they know about it? On a high level, first of all, to make it absolutely clear, the model and the parameters of the models do not change at all. So the symmetry only uses symmetry, so any adaptive attack would need to use symmetry, right? So from a high level point of view, what we have is that this defense is based on a, so to speak, shortcoming of CNN. So it's quite fundamental to CNNs. And so unless this gets solved, there isn't much that the attacks can do. And I'll explain why. Since we use no other changes to the model or parameters, they will have to use symmetric images in their optimization, the attacks, which means that for their loss functions, they will need to use the output of these symmetric adversarial samples, which, as you increase the perturbation, the output of them is going to be unreliable, and even more so since there's increased perturbation and the samples keep getting closer and closer to the classifier boundary. So having conflicting outputs for symmetric samples is going to make these attacks not able to optimize and to optimize their attacks and to have optimal adversarial samples that they converge to. And actually, from experiments, we have found that actually we are able to obtain better results for adaptive attack because of this, compared to an attack that is not aware of the defense. Now moving on to XGBoost adversarial perturbation attacks, which is the other paper related. Here I'm showing the FNIST dataset simply because it's these these classifiers are mainly used for non-image data. And so it's hard to convey or to show in a figure, if it's a data set that is non-image. How do you show just a feature? So I'm showing here the FMIS. So these classifiers are basically decision trees. So they are different from CNNs, also in the sense that they are not differentiable functions, and accordingly they have a different set of attacks that apply to them. And these are very much used for example, virus and non-virus files. And there was a question in the Q&A. So yes, this is very much relevant to that question, in that this defense would be able to defend these classifiers of virus classifiers. One challenge in these when you classify such data sets is that you no longer have the symmetries that come with images. So the only, one symmetry that I used in the previous paper, but also here, is this inversion, which means that since the features will range from 0 to 1, what you can do is go from a feature value to 1 minus that feature value in order to gain one symmetry. An additional thing here is that unlike CNNs, XGBoost classifiers have not been studied as much, and especially adversarial samples or adversarial attacks are not even remotely studied as much as adversarial attacks on CNNs. And this may have to do with the fact that in CNNs you can actually see, or you can attempt to see or convey such attacks, but it's harder with non-image data. In any case, in order to be able to apply this symmetry defense, I looked first into whether these classifiers are actually, do they have this inability to handle symmetry well? And it turns out that they also share this with CNNs. So they are also, for example, the experiment was that we train a classifier with both original data and inverted data. And then you try to classify original with a testing data set. You try to classify original samples and then inverted samples. And do they agree? Is there any disagreement between the two? And actually, yes, for all the data sets that have been considered, there is a disagreement, which tells us, again, as in CNNs, that XGBoost classifiers are not good with symmetry either. They are unable to handle symmetry well. Jumping straight away to results, this is the results for the zero knowledge adversaries, and I'm highlighting here, there's many, vertically there's different kinds of data sets, and you can see different types of attacks, 6 types of attacks. And I'm focusing just on one, NIST, which is kind of a more well-known data set, but the results are similar for the other ones. So basically, in the two upper highlighted rows, you can see that the default and the robust defenses for most of the attacks actually result in 0% accuracies. By comparison, the symmetric defense goes very close, or even exceeds the default classification of 98.2%. And the robust defense here uses it's basically adversarial training, but they call it robust training in XGBoost related classifiers. So yeah, we have good results also with the zero knowledge adversaries. Another thing that I haven't included here, but I thought I'd mention, is that something different in XGBoost is that from the experiments, we see that Some attacks, the MILP, LT attack, and Cube, actually can become unable to attack even just by using symmetric samples. And so this is kind of unexpected, and it is not explored more in the paper, but probably we'll explore in the future that why these attacks are basically not able to. And these are the attacks that look for adversarial samples kind of closer for lower perturbation. Whereas the other ones, the opt, sign opt, and hop, skip, jump attack, they are able to construct. So yeah, there are things still to be explored. Now, moving on, this is for the perfect knowledge adversaries. And in this case, I'm able to conduct experiments only for the FNIS dataset because more symmetries or another solution needs to be found for non-image datasets in order to apply this defense against perfect knowledge, against attacks that know about the defense. So here again, we can see that with default and robust classifiers, we can get down to 0% accuracy, basically, for most of the attacks, whereas for the defense is able to go to over 95 or even over 97. So yeah, we are able to, well, even beyond the original classification. So yes, we are able to recover the correct classification even in the XGBoost classifiers for perfect knowledge adversaries. Now, in conclusion, we have that we are able, as I just mentioned, we are able to obtain quite good accuracies, and we can go from zero knowledge to perfect knowledge adversaries. And as I reasoned and showed for CNNs, we can counter adaptive attacks that are aware and try to actively adapt against the defense. Related to what I mentioned originally in the first slides, what is important is that for this defense, we do not need to know the attack in advance. So we are able to counter different attacks, and this makes it very applicable to real attacks in the real world where we wouldn't normally know the attack or its perturbation. And since another plus is that there's no changes in architecture or parameters, so the only additional thing is training with symmetric samples, more symmetric samples. And another plus is that the accuracy of non-adversarial samples remains the same, and actually the treatment that we apply to both adversarial and non-adversarial sample is exactly the same, so we do not need to know whether an incoming sample, is it adversarial or not. We do not need to have prior knowledge. And I just wanted to mention, we related to this research, we have already received funding from Business Finland for starting a startup project that is going to be based on this, or have this as a starting point, but also try to focus on wider range of topics, robustness and security of AI, and also privacy as well. So any questions? Thank you for your attention, and any questions?